In this video I'm gonna show you the measurements of this coil, and I will also show you how the inside high current coil and the output current coils are made, because there were some questions about that. Hi, my name is Ivo. I'm doing open source research into free electricity for all, so we can have 24/7 free power. When looking from the side of the coils, this is the picture you'll see. In the center is the high current coil. Close coupled around it in blue is the output coil, which serves as a capacitor plate for the high voltage coil, which is the green on the outside. And there's a larger gap because of the high voltages, and that gap prevents spark over. So here we have the two coils. This is the high voltage coil, which will become series resonant with that strange bulb because of the way it's wound. And this is the other. These are two coils. Top one is the middle, is the coil that will be series resonant with that coil by its capacitive coupling. And the center coil is the parallel resonant coil, which will have a parallel capacitor to tune it. As you can see, I've got 6 windings that are all paralleled to make a strong capacitive surface, and I've done the same for the middle coil. So these two coils are exactly the same, and they follow along the pitch of this coil. So that's the same pitch here. I believe it was 15 millimeters for this one, and they slide into each other. But first I want to do some measurements while they're separated. And this is, by the way, the induction stove coil that I used for the center coils. I used 6 of these. I cut them in half, so I wound all the wire off and I cut it in half, and then I made the windings. So 6 in parallels for the current coil, 6 in parallel for the center coil. I used this because the wire is multi-stranded and each strand is separately isolated by enamel, and there are 18 strands per wire, so times 6 in total per coil. That's a lot of surface area that can be used for the capacitive coupling. Now here is my meter. It's a Unity UT612 LCR meter. Let's measure that high voltage coil. So by itself, nothing inside, nothing is coupled, just to see how much inductance I've got. And I'm going to do all my measurements at 100 kilocycles per second. So let's do this measurement with the frequency on 100 kilocycles per second, and it measures 10.685 millihenries. There it is. And now the center coil by itself, well, it is of course coupled to the high current coil in the inside. So this is the blue winding, and this is also the blue winding. I leave the other coil open-ended, and this one measures 7.669 at 100 kilocycles per second, and this is microhenries, so that's a factor of 1,000 smaller. And then the current coil, which will be slightly less due to its smaller diameter. Again, the center coil is now not connected, and this one measures 7.48 microhenries, a little bit less due to its smaller diameter, but it's comparable. Now I'm gonna slide these coils into each other, but first let me measure the capacitance between those center coils. And to do this properly, I will short them out so they can really behave as capacitor plates. Okay, so the coils are shorted out, and this makes it so that there's no voltage difference between the ends of the windings. So they act as capacitor plates with equal voltages. So I will again connect my meter. This time I connect them to both coils, one on each lead, so they act as capacitor plates, and this should be a fairly high capacitance because they're close coupled. At 100 kilocycles per second they measure 2.626 nanofarad. Okay, now I will remove all those connections again, and I will put the coils into each other in a way that makes sense. And what makes sense is that this coil will match that coil, that it mirrors it, that it will act as a capacitor plate that has the closest proximity to the coil. So here starts the coil, and here starts the red coil. This is my marking. So I will line these two up, and then I will measure the capacitance between those two coils and see what I get. So this is the open end. So this is here, this is there. Then I should connect it like that. and I match it up and I build it this way so they should have the maximum capacity. Now I will measure the capacity to the blue coil, so the center coil. So I'm gonna short this one out also so they can really act as capacitor plates. No voltage developed over them. I'll hook up my LCR meter to the coils, so the center coil and the high voltage outside coil. And then I'll measure again at 100 kilocycles per second, 318.8. Okay, so we have now the capacitance between the center coil and the outside coil. So now I will measure the capacitance between the inside coil, the high current parallel resonant coil, and the outside coil, the high voltage series resonant coil. Okay, I shorted out the high voltage coil and I shorted out the high current coil and I open-ended the middle coil. And I now measure 296.8 picofarads of capacitance between those two coils that are nested inside each other. And the middle coil is just floating. It's not playing any role. And what I did is move those coils up and down and around until I got the maximum capacitance, because these coils should be aligned perfectly and then they give the maximum capacitance between them. That is when I did like this, so it's sticking out a centimeter over here, and I drew some lines so I can always check if it's aligned, because now I know my capacitance is maximum 296.9 picofarads between the high current coil and the high voltage coil. I am going to hook up my LCR meter to the red coil, which is the inside coil on both ends. So I'm measuring the inductance now while the other coils are open-ended. The high current coil measures 10.910 microhenries. If I now short out the center coil, which is the blue one, then the inductance should change, and the amount of change will be an indication of the coupling factor. As you can see, it has a strong coupling because now the inductance is measuring 1.128 microhenries, and that's a lot less. And there's a formula that can be used to calculate the coupling factor. Let's first do something else. We are measuring still the high current coil. So now I will short out the high voltage coil and see what the coupling factor is there. So I'm still measuring the current coil inductance, and now I've shorted out the high voltage coil. And as you can see, it now measures 2.426 microhenries. This means there's still a strong coupling factor between the current coil and the high voltage coil on the outside, but it is a little bit less because the inductance is a little bit higher. Now we do it in reverse. Now I will measure the inductance of the high voltage coil. Let's see. And it measures 10.88 microhenries. And this is with the coils open-ended. So now I'm gonna first short out the center coil, and that's the blue coil, this one. So I'm going to short it out, and the inductance of the high voltage coil now drops to 2.22 millihenries. Millihenries is of course 1,000 times bigger than microhenries because we have got a lot more turns. And now I will short out the high current coil and leave the other coil open-ended. So now I'm going to short out the red coil, this one, and the inductance now measures 2.599 millihenries. So now let's measure the center coil just to compare it and see if the measurements and calculations have a matching result. So I'm hooking up my meter to the center coil. I'll remove the shortcuts over the coils, and it measures 11.494 microhenries. Now I'm going to short the high voltage coil out so we can calculate the coupling factor there. It should be the same as we calculated before. The center coil now measures 2.033 microhenries, so there is a pretty strong coupling. And now the coupling to leave the probes, and I short out the other coil, so the red one, the high current coil, which is now shorted out, and the inductance drops a lot further. This means that the coupling is very strong, which is also predicted 1.107 microhenries. So very strong coupling factor there. Now the coupling factor is important. It can be between 0 and 1. And 0 basically means there's no coupling between the coils, and 1 means that they feel each other 100%. So this is the triangle in which I will fill in the data. We've got HV for the high voltage coil, HC for the high current coil, and OC for the output coil. First, the capacitances. The 318 picofarads is series resonant with the high voltage coil, so the output coil OC acts as a capacitor plate for the high voltage coil. As you can see, the capacitance between the output coil and the high current coil is the highest, 2.63 nanofarads. And this is of course because they are very close coupled. They're wrapped on top of each other. And these are the inductances of the coils by themselves, with the other coils being open-ended. And now added in brown are the inductances of the same coil, but with one of the other coils being shorted out on itself. As you can see, this lowers the inductance. And using this formula, we can now calculate the coupling coefficient K. And here are the coupling coefficient values in red. I grouped them in pairs of 2 so you can compare them, as they are different measurements, and as you can see they're very closely matched, which tells me that it is a proper measurement. The strongest coupling is of course between the high current coil and the output coil, because these are rolled on top of each other with barely any spacing, and K of 0.95 is to be expected. And the other coils are also fairly high in their K factor, and this is good because then the dual resonant frequency splitting mode will have a high bandwidth. One other thing, all coils are wound the same direction. And this makes a lot of sense if you look at the energy flows of the displacement current and the magnetic current, because they need to flow in a way that they don't disrupt each other. I got a lot of questions about how to roll the high current coil in my last video, so I thought I included this in this video. The pipe needs to be made the right diameter, as I explained in that video. Then you put on the right pitch to fill up that coil. In my case, I used wires from the induction stove coils, and these are 2.5 millimeters wide. So I got it off and I cut them in half, so each coil had enough length of wire to cut in half, and this is 1/2 of such a winding. And I measured the diameter of this, and it's 2.5 millimeters in diameter. That means when I have 8 of these coils in parallel, like so, 1, 2, 3, 4, 5, 6, 7, 8, and I place them side by side like this, then it will need a total of 2 centimeters, and that will be my pitch. So these lines correspond to the width of all these coils together, and I choose 8 for my next coil. So this is much too wide. This is just a test tube. But my other coil, which I showed in the video and which I use in my experiments, has only 6 of these windings in parallel. And thus I have 15 millimeters of pitch, because they all are side by side. Now what I did was just start laying the coil with some extra end, of course, to connect it all up, and taped it all down with simple tape. That first layer, of course, is very important to follow that pitch, and that's why I made those lines. So I tape it all down and I go across the lines like so, and I fill it completely up. That will be one length. Then I take another one of these coils, because I need in total 8 if I want a 2 centimeter pitch. So 4 of those coils cut in half, giving 8 of these windings. And then I just wrap it side by side by side by side until I have 1, 2, 3, 4, 5, 6, 7, 8 of these wrapping around that coil, having the same pitch of 2 centimeters in this case. So they all start at the same point and they all match up like this. So it becomes a flat coil. like so. These are a little bit more than 8, but this flatness has a lot of capacitive coupling to the other coils, and that is why I do this. Also, it is per winding, it's 18 strands, so it has a lot of surface area, which adds to the capacitance. So when these are all together bundled, whole coil will be filled up and it will look like a lot of windings, like several hundreds of windings, but in reality, you only have 1, 2, 3, 4, 5, 6, 7, 8 turns in this case, but probably a little bit more when you have 2 centimeters, because this is a little bit wider than 2 centimeters. In the case of the 15 millimeter, you will have even more windings, but they are all in parallel together. I hope this is clear. Now, if you finish that, then you take Kapton tape, which is very good for heat resistance, and these coils will carry loads of current, so they will heat up. And you place a layer of Kapton tape over the whole coil. And I did 2 layers to be safe, to get a proper surface area. And then I do the same again, exactly the same. I draw the lines again and I match everything up. I again start with 1 winding, I tape it all down, and then the rest of the windings are one by one rolled and filled up, so the pitch becomes fully covered with the windings. Again, if you use 6 on the current coil, then you use 6 on the output coil, and they sit wrapped tight upon each other. That's it. That's how these coils are made. And of course, the endings then, one side is cut, so you need to get that enamel off. I scraped it off with a knife, and the other end I can still use because it has a proper connection. I can bundle these all up. I kept these, then I used this to bundle these coils up, because I would have 8 of these together, and I put all 8 in here, and inside they're all connected. So then I have just one connection. It will become one coil, and the other side is also connected all up together, and then you have a very low inductance coil because it has only a few turns, but the coil itself has a large surface area where it can couple to the other coils, and that is essential if you want to use displacement currents to power your load. Now finally, when the 2 coils are finished, you again get that Kapton out and you roll it over the output coil, which sits on top of the current coil. And you roll it completely, you fill it completely up. So then you can fit these coils inside of the high voltage coil. You just slide it in and you will notice you will have a gap. In my case, my gap was 2 millimeters because I want to be able to have very high voltages. And I filled this gap up by rolling tape over the coils over and over and over. Just roll it over the coils. And you need a lot of this because this is very thin tape, and I ran out and I ordered new and it didn't arrive. So I changed to this tape, which is polypropylene, which can handle high frequencies, although the glue might not, and that might be a problem, but I took a chance. So then the tape fills up the 2 millimeters on top of the coils, and then the coils can tightly fit into each other and become one. And then you get something like this, which I built in a few days of time. So the high voltage coil is the thin wire, and you have this is one coil. This is the high current coil because I coated red, and this is the output coil, which sits on top of it in the middle, which is blue. And they're all just bundled together. I used 6 of them. 1, 2, 3, 4, 5, 6. And the other side is also bundled together. I did this a little bit different because I had the connections there. So just got a screw and I tied it again in this to be able to connect it to the other parts of the circuit, because high currents will flow. And then the coils are finished and ready for measurement and for tuning and testing. I work open source, and this means that I provide all the information that is needed to replicate this, and therefore I make these videos for you all, so we can all have free electric power. If you want to support this research, you can join this channel and become a channel member. You can also support this research by giving a donation on the PayPal account that is listed here. That's it for now. Thank you for watching and see you next time.